Birds flying high, you know how I feel. Sun in the sky, you know how I feel. Breeze drifting on by, you know how I feel. It's a new dawn, it's a new day, it's a new life for me. And I'm feeling good. I'm feeling good.
Ladies and gentlemen, welcome to this evening. Thank you all for coming to this, our first annual awards event. My name's Louis. I'll be your co-host for this evening, alongside my good friend and colleague Shay. Lose the hat. Lose the hat.
So, over the past year, our society has made substantial progress and succeeded in a wide range of engineering projects.
Tonight is an opportunity to look back on those projects and recognise all that made them possible.
Without our incredible team, we never would have been able to do some... There we go. Scale Up Project Odyssey, giving students the opportunity to progress themselves from bronze, silver, gold up to the UK RA L1 rocket licence.
Launch a mid-powered rocket in line with a customer brief with the UK SED charity in the NRC competition.
Launch a fully functional drone with the UAS team, which was able to compete and fly quite well.
And finally, make a high-powered rocket up to 2,013 metres with the MAC team.
Which beats Sheffield.
Expecting nothing less, obviously. We'll then hear a little bit from a couple of guest presenters. So we have Paula Gill from the Northwest Aerospace Alliance.
We have Fred Eastham from the IET
and Professor Robert Walsh, our Assistant Pro-Vice Chancellor. And then after that, we will have the thing you're all here for, the awards. But first, will you please welcome Mr. Professor Robert Walsh, the Assistant Pro-Vice Chancellor.
And these rockets here, which is probably a good thing, actually. Good to see you. As I said, my name is Professor Robert Walsh, and I have the pleasure to be the Associate Pro-Vice Chancellor here at the university. And they wanted me, with the guys here, to just give a wee bit of context to what's going on, but also to sort of start things off in its right foot and right way. It's interesting. You probably wonder what am I doing here? Well, I'm actually an astrophysicist. I also have most of my degrees and PhDs are in applied mathematics. What am I doing here talking about aerospace and engineering? Well, one of the reasons, hopefully, is this one. Because I work with NASA in particular for the sounding rocket program. That's suborbital rocket launches, which some of the guys in the team, in the aerospace team, have been involved with, particularly looking at sending instrumentation up to observe the sun. That's my area of expertise, and trying to understand how the sun actually operates. We learn a lot from these suborbital flights. So great to see what we're talking about this evening and what's already been done so far. So one thing I thought when we're looking at this, and when you're trying to think about what's going on, there are some things that we all share. And particularly if I'm talking more to our students and people who are associated with you here tonight, is that we all hopefully share that curiosity of things we don't understand, things we don't know, and things that we really want to find out. And that doesn't matter whether you're doing a computer simulation or you're trying to create some new art, as we do here at the university, or maybe you're sitting in the lab working out a new biological approach to some sort of virus or something like that, or whether you're sending rockets into space. It's all about that little gem, that little germ of curiosity setting you off in order for you to understand the world around you. And I hope that as you come to university and you're part of what we're trying to do here at the University of Lancashire, that curiosity is something that is enriched and enhanced and hopefully satisfied if we manage to figure out what's going on. This is what I spent my days as a researcher looking at. This is an extreme ultraviolet image of the sun. This is really what your star looks like from space in extreme ultraviolet light. The gases that we see here are really electrified gases of plasma, round about 600,000 degrees. And we try to understand how that star actually operates and how it works. And these rockets that we were involved with was trying to take some of the best images that we could ever have of this particular object, something people hadn't done before. Oh, there we go. There you are. Well, one thing we found, and one thing the guys maybe wanted me to sort of say about and give you a bit of encouragement, is that wherever stage you're at, okay, whether you're starting your degree and this is your first year here, or maybe you're part of the way through, or maybe in your third year and you're wondering what the heck's going to happen next, or you've graduated and you've sort of gone on. No matter what projects and things that you're involved with, life generally is complex and evolving. Okay? Don't just expect one thing to follow on after another. And that's the core traits that hopefully you're being taught or have been taught here at the University of Lancashire. That's systematic thinking. Taking a problem and breaking it down into its individual parts. Trying to understand how other maybe areas and disciplines, things you maybe don't know fully about, but you could bring into what's going on. And more than anything else, it is that comfort with uncertainty. We don't know everything. That's great. That's really what it means to be at university, to actually learn things you've never come across before, but also to accept it and say, well, look, that's something we can actually work with. Also, I just wanted to say this, and this is part of a similar talk I gave to some postgraduate students not a lot long ago, is that life is not a linear process. And if you speak to any of the people here who are going on in years like myself, if I had said to me when I was your stage that I was standing here and this would be my pathway to actually be a professor at the university or working on the things we work at, I would have laughed at you. Because life is like that. Life is non-linear. It moves in different directions. But you are smart enough to adapt to that, see where the gaps are, and actually move into those gaps and try to understand what's going on. The training we believe you're getting here, and what you've done through the Aerospace Society, what you're doing with the MAC work, what you're doing in regard of McE, and all the other bits and pieces that pull all those together, really is you building up that resilience, that teamwork, that understanding for what it means to step into that non-linear life world. Here's us. This is one of the first launches that we did back out in 2012. It's a long time ago. Some of you are probably thinking you were purely just 5 or 6 years old. Some of you probably maybe even a bit older than that. This was our first one. You can see the crowd of individuals it takes to put just one rocket up, which actually takes about 5 minutes from launch to apogee, about 130 kilometers up, and then another 5 minutes. 5 minutes up there in space, another 5 minutes down, so 15 minutes from launch to landing. And we all had roles to play. And you're learning those sort of things with the programs and things that you're involved with here at the university. And that went really well. In fact, it was absolutely perfect. Okay, so the rocket went right along the rail. The camera worked very nicely. We recovered the payload safely. This is out at White Sands, New Mexico, where these things are actually launched. And then what is the Trinity base? If you've seen Oppenheimer, then this is where we've launched these rockets from the site of their sounding rocket program that NASA has. So that was so good. We got this group achievement award. It was all brilliant. Everybody's patting each other on the back. It's absolutely brilliant. So of course you have to do it again. And this was a difficult second album, where where it's all gathered here again. The rocket is there behind us on the rail. The instrument is in that white box. We call that the shroud. It cools it down against the hot temperatures of the environment. And it launched. But it didn't happen. No data. And if you look at the wee bottom here, you might be far away to see, is that what happened is that somebody screwed in a screw too tight at the back, and it shorted the connector for the shutter on the camera, and the shutter stayed closed. So 2 to 3 years of planning for this. We got funding from NASA to do it. Was sort of lost. And you think to yourself, well, this is a bit disappointing, but you know, rocket science is difficult. Hopefully you guys who are involved in the rocket launches, you see that. You see the, so you know, this isn't easy. If it was easy, then lots and lots more people would be doing it. But that doesn't mean you don't do it. That doesn't mean that you don't get involved in things and you don't strive for what's actually going on. In fact, you know, success is built on a whole host of failures. And if you didn't have those sort of failures, and you knew this as engineers, you didn't try all these things, then you don't actually reach the point where you can actually say, yeah, that's been very, very successful. So always think about that. Always think about the learning that you can get when things don't necessarily go exactly as you would want them to. In fact, there's a famous phrase that says, you didn't come this far to only come this far. Okay? So try and think about those things, the fact that, you know, you can build upon what you've got. And sometimes when you've gone on a journey, even with your studies, and you're trying to work through things, saying, oh, am I really getting through this? Look back at what you have done and how far that you have actually come. This is a very exciting time for the university, but also, I think, for aviation and aerospace and space generally. And we've just opened up a new facility at the university out at Wharton, right beside BAE Systems, which is a teaching, research, and a business engagement facility, which our tagline is Shaping Tomorrow's Skies. And some of you may have actually been out to see us at Wharton and seen what we have out there. We have an indoor fly space. We have you know, it's all complementary to what we have here in our Engineering Innovation Centre. We have classrooms. We're hosting events out there. And I hope if you haven't seen it yet, you will see it this year and get an opportunity to maybe be out in altitude, see what we're trying to do. And it's really those facilities that really are at the cutting edge. They're the opportunities that take you into your careers, whatever that may be in the future. So I'll finish off there. I only want a question. When I did this talk recently, people said to me, well, that's really good, Robert, but did you ever launch any other rocket again? Or did you end in simple failure? Well, we were fortunate enough to be able to launch again, and we managed to actually change the instrument we were looking at and launched fine, and actually produced some of the sharpest images ever taken of the atmosphere of the sun. And that time between the failure and that success was used wisely to produce something which, again, no one's ever seen before. And I feel very proud of the team here at the university and of the wider collaboration we have to be part of it. So congratulations to all the awardees. You're here tonight, and hopefully you're going to have a good time, and this will be something for you to remember. The fact of what you've done, how far you've come, and something for you to build on going forward. But if nothing else, when you're here at university and when you go out and you finish university and you go into your life, stay curious. That spark of, you know, trying to figure out what's actually going on should never leave you. But also just the fact you'll never figure everything out. So uncertainty is something that we need to live with, but it drives us on. And of course, success builds upon any failure. So thank you very much for all you've organised here tonight. I know Louis in particular, but the whole team here. This has been brilliant. We're very proud of what you've done, what you've achieved, and I'm looking forward to see who gets what at the awards tonight. So that's all. Thank you very much for listening.
So, what is the NRC? Well, if you can look up to this little sticky here, it stands for the National Rocketry Championship. It's a competition run by UK SEDS. It's the UK's National Student Space Society. They run a number of different competitions, such as the Olympus Rover Trials, the Satellite Cancer competition, and of course, National Rocketry Championship. So, this is a picture of us launching our rocket last year, and that's what we want to talk to you about today. We want to show you our project from last year. So, starting off with some of the rules from the competition. Well, last year we had a target apogee of 2,500 feet. So the closer you get to it, the more points you get, and that was what we were aiming for. There was also, of course, the fact that we had to carry both a customer and a rideshare payload. Customer payload was given to us by UKSED, and the rideshare payload is something that we designed ourselves. And lastly, we were limited to 130 ns impulse for our motor selection. So those were the three main rules that we had to adhere to. And if we just go to the next slide.
So we decided to name our project last year Project Callisto, and there's a picture of our team right there. So aside from the goals set to us by UKSEDS, we had our own objectives in mind. Obviously, to successfully launch the vehicle to 2,500 feet, to then be able to recover the vehicle and return it to the launch site, to determine the apogee value from Morse code. We have to do this as we were not allowed to have any actual data sent to us remotely from the rocket, and we had to be able to calculate the apogee upon finding the rocket. Also had to recover the flight data post-launch when we were allowed to actually look at the data that our rocket picked up. We also had to provide sufficient power to the customer payload as well as our own rideshare payload, and carry the customer's payload within our own rocket design. We also were given a risk assessment by UKSEDS, and we were also allowed to add our own risks to it, and we had to adhere to it in order to have a safe experience. The flight data had to be presented after the rocket was recovered. And there's a picture of Louis figuring out the rocket on the launch day.
Right. There were 48 major aspects to designing this rocket. There was, of course, well, the design section, the manufacturing portion, the avionics needed its own team, and of course the submissions that we had to regularly deliver to UKSEDS. So starting with design.
We use a software called OpenRocket to do our initial designs. That's an early rendition of the design of our rocket. At the top, we have our AV bay, our avionics bay, in the nose cone and the shoulder. Underneath that, we have the customer payload, which is the circular object. And then we have an eyeball running all the way through. This is what holds our rocket together when the parachute has to deploy. The parachute's also there in the middle, and at the bottom is our motor with our fins and our motor retainer. Using OpenRocket, we were able to simulate the maximum apogee. We're also able to alter the design of our rocket in order to keep it within the stability margins of 1.5 and 2.5. Any lower and it's too unstable on launch, and any higher and the trajectory, if it went off slightly, it continued going that way. That is a simulation for our stability. It shows the stability margins and the location of the center of pressure and the center of gravity. We had to keep a velocity off the launch rail of at least 20 meters per second, as per the UKSEDS rules. And that is a simulation of our flight path, our altitude, our acceleration, and our velocity. We were also able to tinker with the motor and injection charges to be able to get them to a time at which we were able to achieve the maximum apogee and safely recover the rocket.
So one of the first designs that we'd like to talk you to about is the fin can. So here you can see some of the CAD pictures that we have of the fin can. One of the designs we opted for was filleting the fins. This just reduced the stress on the fins, and the retainer, which is threaded. The reason we decided to go with the fin can in the first place and not just stick the fins on the body tube, well, we were a team of mainly first years last year, so we were expecting to make a lot of changes to our designs. And making a more modular rocket like this, well, we can make the modifications a lot easier without affecting the entire rocket's design. If you just switch slides. Yeah. We also had two main iterations of the design. As you can see in this first picture, over to the center, it has quite a complicated design to keep the motor from flying right through the rocket. So we simplified that down over in this picture to just a single beam. And in the first one, we only had one hole for an eyeball. This would be connected to the shock cord for the parachute. Decided to go for two holes, disperse the forces, and just increase our factor of safety.
For the customer payload, we had to put it inside of a casing. We were provided a model by UKSEDS, however, we were allowed to make alterations to it. This is our initial design. It was a two-part casing of the bottom and the lid. However, we decided against using this one, as you can see from the testing there. It was too structurally weak to conform to the testing, so we decided to go against it. and instead we used this one, which was our updated design, which we use in the final rocket, as you can see there in the assembly. The payload would just go inside, and then there'd be a little lid to keep it in place. The holes along the side, we assumed there may have been a camera on board, so we put holes in the side to accommodate for the fact that there may be a camera. The casing is made to be the exact diameter of the tube, so that all the fumes from the motor, when they go up, wouldn't damage any electronics. There's also 4 holes in the top to put threaded rods through in order to hold it to the AV bay.
Yep. Our nose cone was optimized in Open Rocket for the maximum apogee, and if you remember back to the initial Open Rocket simulation, the avionics bay is primarily located inside of the nose cone, so you can just see the rails in that section view of the pad over there. We also have the pitot holes just above the shoulder for the nose cone that allows the air to come in and hit the sensors that we need on the avionics bay.
Over to the manufacturing. Me and Hussein were the manufacturing members last year, so we were tasked with making all the components, putting the rocket together. The majority of it was made through 3D printing, as it was an easy resource to access within the school, and it also let us prototype new designs quickly, so we were able to go through many different iterations and many different tests before settling on the final model for the rocket. There is a video there of just us doing some work in the workshop.
Yeah. Testing was another responsibility of the manufacturing team. We began using FEA to just double check all our components met the requirements set by UK SEDS. As you can see here, we were testing the fins deflection, but the requirements suggested that we use physical testing, which we did here. Our simulations were accurate, thankfully, and everything was within the requirements set by UK SEDS, so we're good to keep going with the manufacturer. And lastly, production deadlines was also a responsibility of the manufacturing team. Here's a Gantt chart that we had made, spanning from the start to the end of the project. Manufacturing begins around about a month into the project. That just allows us to rapidly prototype any design iterations we come up with. And on the Gantt chart, we end manufacturing roughly in the penultimate submission that we sent to UK SEDS. In actuality, manufacturing kept going all the way up until launch day because there's always improvements to be made.
Penultimately, we have the avionics. The avionics was designed by our students in KiCad, which is a free software we used to design it. We sent it off to be manufactured by an external company. We included a pressure sensor, a temperature sensor, and humidity sensor for our data points to be logged. And we also used an accelerometer to see our velocity. We used a 3.3 volt voltage regulator for the sensors and a 5 volt one for the customer payload. This is where the avionics was housed, with 4 clearly marked points on the avionics bay, which would then fit to go into the nose cone.
We had 4 major submissions to deliver to UK SEDS, beginning with the recorded presentation, the preliminary design review, as pictured of Tay doing his side. It was followed by the critical design review, which was due sometime in February. This was a 30-page documentation, which finalized some of the design ideas we had come to. Yeah. Another was a manufacturing review, another recorded presentation. Here, the design of the rocket was completely finalized, and we were just simply showing how we would manufacture the rocket and if it was feasible. And then in the weeks leading up to the launch, we had the flight readiness review, which just showed that we met all the requirements set by UK SEDS.
There's a video there showing how the assembly was put together. There's supposed to be well. Yeah, so that's just how the rocket was all coming together. In the top right, you can see the final model of the rocket, which we also have in front there in the middle. This is our final open rocket design. We decided to make a few alterations near the end by making the rocket shorter in order to have the centers of mass and pressure be better aligned and also to remove some of the weight. And that is how it all came together in the end.
Yeah, so this is our rocket launch day, and here's the video of us launching it.
Okay, working on pad 4.
Alright,
Heads up first flight, please. Pad 4. Clear skies. 3, 2, 1.
Yes. All right. Please deploy. Deploy. As you can see, really excited. It was a successful launch and a successful recovery. There's a very lucky picture of our parachute, and as you can see, there were improvements to be made. So we did include 2 holes for the eye box in our second design iteration of the fin can, and that was a very good idea. One of them popped out, so if we went for the first iteration, we wouldn't have a rocket after test launch. And also, if you can see on that picture over there, the nose cone just split right in half, so that clearly needed some improvements. And there's our final launch rocket. Another successful launch and an unsuccessful recovery, somewhere in that field. If you just go to the next slide, that is what we found after, I think, 2 hours of searching all of the rocket with none of the data. It turns out we had a failure at the customer payload. If you just go to the next slide, that is recovered 3 days after launch, and it turns out, if you look over here, our customer payload is the exact same one we used in the test launch. We had forgotten to reprint it, and that one had already been through all of the force of the test launch. Everything else was brand new, except for that one part supporting the entire parachute. I mean, it's kind of disappointing. I mean, all that effort put in, but it was such a learning experience, amazing fun. But we're looking to improve upon all of this next year.
Yeah. So this year we've doubled our size to 20 members, which means we've had to split into 2 teams, Team Belka and Team Strelka, which we named after the first 2 dogs to go to space, orbit the Earth and come back safely. We're looking at making a lot more improvements from last year, a lot more test launches, a lot more organization, and yeah, I think that's it for us. Just a quote to finish it off with.
So the only limit to your success is the amount of effort you put in. And the only reason our rocket failed is because we overlooked that. This year we're not cutting any corners and we're becoming a lot more organised. So if we put more effort in, we're going to get more success out of it. Thank you for listening.
Thank you very much.
Sorry for the technical issues.
Thank you very much, Matej and Hussein, for that presentation. Really good work. The really good work that team does. I think they do some of the best work of the teams.
You are leading that team, right?
And moving on, we are now going to introduce our Mac team for their presentation.
Yeah, so you've heard from mid-power, so we're going to up the ante. We're going to hear from high power. So please welcome Alex Morrison and Tyler Moses.
Can you hear me? Guess so. All right.
Mine on as well. There we go. Well, hello, good evening, everyone. My name is Tyler. I am last year's CFD associate for the Mac 25 team, and this year's project manager and CFD lead. And I'm here with.
Yeah, my name's Alex. I was the project lead for last year, and I've come back this year as a mentor.
We're just going to talk to you a little bit about what we did last year in Mac 25 and what we're currently doing in Mac 26. So, what is MAC? MAC is the UK's premier high-powered rocketry competition, and it's held by Exotopic in Machrihanish in Scotland. And if you don't know where that is exactly, it is about a 7 hour drive up north past Glasgow down the west coast of Scotland. It's actually closer to Northern Ireland. So it's where over 20 universities compete, where the students have built a range of different rocket designs in different categories to ultimately achieve the goals of whatever the category corresponds. And not only is there many incredible launches across the week, there is also so many opportunities for space skills workshops, guest lecturers, and a lot of networking as well. So overall, a really, really good opportunity.
So we're going to show you a bit of a video now. We thought we were going to try and make a video to show you how good Mac was, but Exotopic have kindly done it for us. So we're going to show you that video now that explains really well what the competition is, what the different teams do, and it's also got some really nice footage of us and the other teams launching.
These rockets are unbelievable.
Mac 25 is just a fantastic competition. Exotopic really go all out.
It offers something that you won't be able to achieve anywhere else.
It was unreal. We were so excited. Like, I'd say we've learned more here than we did the whole year. preparing for this.
The Mac X Rocketry Series is a competition for university rocketry teams to build rockets. They'll launch up to 3 kilometers here in Machrihanish, Scotland.
It was really rewarding, the work that we've put in this entire year, seeing it just go beautifully straight up.
The rocketry community is so friendly and welcoming that it's not a scary place to join, and everyone's willing to help each other.
The more experienced teams lend a hand and share some of their equipment and teach them a few things. So it's a real great skills transfer between those who know about it and those who are just getting started.
There's not really many people, even on aerospace degrees, that can say they've worked with active rocketry systems, and that's an opportunity that this competition gives you.
As I see the technology that's built into these rockets, it is so sophisticated.
These guys can carry on through the ranks and pass on their knowledge to incoming students, and we keep that flow going through universities, and so we'll have a bright future, especially here in the UK.
In every job interview I've done, all I talk about is rockets, and they love to hear it because it's so different to what anyone else has to say.
They may be launching to 3 kilometers this week, but in their future of their career, it's very realistic that they'll be working on rockets going into space based on the skills that they're learning here at Mach 25.
It's the best part of the competition, really, seeing all those students leap with joy when they launch their rocket.
I think it's the sound. It might be because we're so close to it and you get to see it launch, and it's just really cool to see that we kind of made something that's gone so far.
We've launched a rocket, recovered our rocket, which is amazing, and it's just been such an incredible time.
I think we're going. I think we're launching.
5, 4, 3, 2, 1.
So, a couple of sort of key points from that video, from our launch. So the MAC competition aims to launch high-powered rockets to altitudes between 2,000 and 3,000 metres. You're scored on how close you can get to that target. So it's not just about who can make the rocket fly the highest, it's who can achieve a very precise target with no control systems. So there's a real mechanical challenge. The rockets have to carry a payload. For us, that's the nose of our rocket. That's a 1 kilogram plus CANSAT payload. For us this year, that was imaging on our own custom-built GPS systems. And there's opportunities for Category 2, like the rocket next to me, but also for Category 3 rockets, which are things like 2-stage rockets, cluster designs, and more advanced prototypes. So this is sort of how we've progressed through the 3 years of this competition. So we started at Mach 24 with a relatively small team and a 1,500 metre target. So that rocket is actually on this table. It's the yellow and green one here next to me. So we achieved 1,273 metres with that rocket, which we're really proud of. And then moving into Mach 25, we've taken that knowledge and that experience and aimed for 2,000 metres with this fully carbon fibre rocket next to me. So of that, we managed to achieve 2,013 metres. So by the accuracy margin, we're currently the most accurate student-built rocket in the UK. No one at the competition even came close this year, which was absolutely fantastic. And then hopefully for Mach 26, we'll be aiming for 2,500 metres with a 2-stage design, and that's again to be achieved. So this is some footage from our actual launch from the cameras on board the rocket. First you'll see some boxes around the image, and that's the AI payload in the CANSAT, actually detecting terrain features as the rocket goes up. And the hope is to hopefully use that to affect the rocket's guidance next year. And then we switch to our main camera, and about 18 seconds after launch, we get parachute deployment and CANSAT deployment. And some really fantastic images.
So this is a visualization of our flight path thanks to our CANSAT payload. So we did, as Alex mentioned, surpass our target altitude, but not by much. So we did hit 2,013.49 meters. Prior to launch, you do need to simulate your rocket in some capacity. So we used a software called Open Rocket, and then we hit Mach 1.1 during flight, which was really, really cool to see. And then, although it was an extremely successful launch, we did have one error during flight, and it was where our main chute deployed at apogee, as opposed to our planned 200 meters. But as far as errors go, the rocket being a bit too safe is one of the better ones, and at least it didn't detonate in the sky, which we did see in Mach 25 thanks to Kingston. So this early parachute deployment did mean that our main body did drift 2 kilometers away and landed in a not so happy farmer's field. But thankfully, our CANSAT deployment was successful at 200 meters. At 500 meters, and then landed only 200 meters away from us. So overall, it took us 10 minutes time to locate on our GPS systems, both our nose cone with our CANSAT and our main body with our AV bay. And then overall time to recovery was 45 minutes, as we did have to go for a little drive to retrieve our main body.
So I'm going to talk to you a little bit about how the competition is structured from the university side. Because obviously all the videos and the images are really cool, but the most important part of the competition is what the students can learn from it. Myself, having done 2 years of this, and I'm sure anyone else in the team that's had any experience with it will assure you that the amount you can learn from projects like this and the events like this is absolutely massive. So we have 5 main teams. They're design and manufacture, propulsion, CANSAT, avionics, and CFD and analysis. So design and manufacture works to actually affect the design of the rocket, its aerodynamics, its structure, and its base drag profile, which are always really important for the altitude target. They essentially bring everything together to make sure we have a really high-performing system. Propulsion manages all the aspects relating to the rocket's power plant, its motor, which is a really big deal because our motor kicks out about 1,000 newtons of average thrust over 2.3 seconds. So designing a mount that can take that is a real engineering challenge. CANSAT is almost an independent team. They design the rocket's independent payload, so it has to have its own power systems, its own flight computers, its own independent and redundant tracking systems as well. And then avionics, similar to CANSAT, do essentially a really similar thing, but that's managing the tracking of the main body, managing the deployment events. There are 7 small explosive charges within the body of this rocket that all need to be perfectly controlled for the launch to go well. And that's avionics' main job, as well as actually launching the rocket and providing any sort of subsystems, imaging, AI imaging, that sort of thing that we might have. And then finally, CFD and analysis work on airflow simulations, and that's really important for things like stability factor and flight safety, so we have a safe and secure flight. So this, again, about progression, is where we've been with Mach 24, so you can really see the size difference between our 2 designs for Mach 24 and Mach 25. I'm not going to get super into the technical aspects, but you can see just how much of this large rocket is taken up by its motor section. And then hopefully moving forward into Mach 26, we have the same design for our propulsion section on the Mach 25 rocket being used as a lower stage for a 2-stage rocket, and that will allow us to go higher, go faster, and hopefully to again achieve that really precise altitude target.
So just to round off, these are our Mach 26 aims that we're going to try and achieve this year. So first of all, we want to compete in Category 3, which is the innovation stage, as Alex mentioned, which is a step up from last year, which was Category 2. That leads nicely on to our second point, where we want to launch the first successful 2-stage rocket at a Mach X competition. Competing in Category 3 means we do have that bit of leeway with target altitude, so we can go up to 3,000 meters. So our target this year is going to be between 2,500 and 3,000 meters. And then finally, we do want to improve our outreach and engagement this year, as we feel that's something we lacked on and we did lose points on last year. So we want to get out there and try and show people what you can do whilst you're still a student, and potentially then inspire the younger generations.
Brilliant. Thank you very much for listening, guys, and please enjoy the rest of the awards.
Cheers, thank you very much.
So, thank you, Tyler and Alex, for that performance.
They really launched that idea.
Yeah, no drag either.
Anyway, what we have next for you this evening is a little bit different from what you've seen so far, but by no means less impressive, just a slightly different vein in aerospace.
No, yeah, not at all. They, in fact, share our knack for self-disassembling aircraft.
Very true, very true. So will you please welcome to the stage UAS.
Thank you very much, Louis and Shay. So, you've just heard a lot about rockets. Now we're going to move over to planes. More specifically, unmanned aerial systems. Now, some of you may not know what they are. They are automatic planes, basically. So all the systems inside allow the plane to fly as it should with a man inside. So this is the first year that our university has competed in this competition, the Armiki UAS. The university has been making aircraft for years, but luckily enough, our team was the first team able to go to this competition through sponsors such as Morrison Project and our mentors being BAE. This is the team that attended that last year with our drone front and centre. So some of the things we're going to go over today is the 2025 challenge, the design, the manufacturing, and the 2026 challenge, that being this year. So I'll pass over to Shireen to explain to you what the Armiki UAS is.
So hello, I'm Shireen and I'm the manufacturing lead for this year's Armiki UAS challenge. So what is Armiki UAS challenge? So it's a competition where undergrads from all around the world design, build and compete with an unmanned aerial system with a specific mission objectives, and the challenges run around. The challenge runs in a span of a year, in an academic year, where there are set deliverables throughout the year. This is designed to replicate a typical deliverables expected in industry when we deliver new design to like a customer. And then the final part of this competition is a live fly-off event where all the students, judges and sponsors come together at BMFA for 4 days, creating a great networking opportunities with companies like BAE, Callan Lens, Leonardo and many more.
So some of the challenge constraints that we had in 2025, which a lot of them carry over to 2026, but there are a couple of changes that we'll cover. So last year, we had to create an autonomous flying device. Our maximum takeoff mass was 10 kilograms. The flight had to be completed in less than 15 minutes. We had to have 20% battery remaining, and we also had to take off and land within a 20 metre by 20 metre box, which is quite a constraint for a relatively large aircraft. This design also had to be simulated in a software called X-Plane, which allowed you to have a look at the physics surrounding the aircraft, which we performed quite well at. A couple more. So this is the example given to us on the day. So here you can see a lot of waypoints. We had to program our drone to pass through all of these waypoints and drop our payload at a certain location. The mission range was up to 2.5 kilometres and it was within a geofence boundary. Our plane also had to fit into a box measuring 1.5 metres by 0.6 metres, so which is quite a constraint when you're trying to take off and land within 20 metres and having a 10 kilo aircraft. We also had to reassemble the aircraft within 6 minutes out of the box, but it wasn't too difficult. This is the design that we came up with after a lot of deliberation last year. It is a high wing twin boom U-tail platform. This design allowed us to control stability of the aircraft, but it also allowed us to take off in such a short runway due to our large wingspan and our Picture Authority. Now I'll pass on to Shireen, who will take you over the manufacturing stage.
So for the manufacturing, we mainly use materials like fiberglass, carbon fiber, wood, foam and PLA. So for the internal structures, we used plywood, bulkheads and stringers reinforced with carbon fiber rods. And the fuselage, the skin was actually made of carbon fiber with wet layer technique, and our wings were formed out of foam and carbon fiber spars, and the landing gear was fabricated using aluminium sheet, and then we had a 3D printed motor mounts. And for the highlights of the competition, we came third in the business presentation and fourth in the explain simulation. And as a first-time competitors, we ranked 20 out of 42 universities, which is a great achievement for us.
So, back onto what I started with. The 2026 challenges brought a few new implications into this project. For the last 10 years, it's been to hold and deploy a payload. This year, we now have to hold and spray water over an agricultural field. We must carry a litre or more of water, and we need to spray this over a 75-metre track. After that 75 metres, we then have 10 metres to stop the water being deployed, which sounds relatively easy, but when you're using a winged aircraft, it's quite difficult because you have to keep a relatively high velocity. So it's an interesting challenge, but we've already started designing and concepting and came up with some solutions for that. The takeoff and landings within the same 20 by 20 metres, but the payload must be inserted from the top. Now, if we look back at our old design, you can see our wings are quite small. Oh, well, never mind, don't like me that way. Our wings are quite small, so we can't fit. So for this competition, we're wanting to put 3 litres of water into our plane, about 3 kilograms, with a maximum takeoff mass being 10 kilos. That leaves us with 7 kilograms of aircraft weight. To fit between those spars, there's about 180 millimetres, which it's going to be a tight squeeze. So this year we've had to increase the chord length of the wings, which has actually helped because it means you've got a bigger lifting surface. But yeah, so it's been an interesting initial concepting phase, which we've just submitted our concept paper for and are waiting to hear back from the IMechE how we did. So this is just a short video showing our drone from last year through the manufacturing phase to the fly-off event. There's no cool music like the others. Another thing to note is that initially we started this competition, so normally universities will start end of September, beginning of October, and they'll run to July. Unfortunately, due to circumstances and students, we didn't actually end up starting this competition until January. So we had from January to June to design, manufacture, and obviously fly this drone. So unfortunately, we had no time before the fly-off event, even though we tried to fly. So going to this competition was the first time we had that opportunity. It was really good. It was a really good event. But as you'll see, not everything went as well as it seemed. These are some of the other drones that flew and deployed the payloads. Just after that, the wings clapped and we collapsed to the ground. But we did get off the ground, and it was a valuable opportunity to learn, which we can take into this year, all of us. Now, these are some pictures from last year. Obviously the drone on the right, but on the left we have it's Falcon Works, but it's our BAE mentors. So James Ritchie on the left helped organise some events for us last year, going over project management and some other stuff. So yeah, it was a really good opportunity to network with companies such as BAE, Callan Lenz, Leonardo, but it was also an excellent opportunity to network with other university students, being able to talk to them and ask them about what their experience has been, and also get help from, which we needed on the day, a lot of help from other universities. So yeah, thank you for listening.
So, thank you very much to Shireen and Josh for that lovely presentation.
Showing our affinity for making self-dissembling aircraft.
Yeah, it's not rocket science.
No, something like that anyway. But now we're going to move on to one of our fabulous guest speakers. So will you please welcome Frederick Eastham from the Institute of Engineering Technology.
Good evening, everyone. I'm Frederick Eastham. I've been around the block, I think, on this aerospace job for quite a while now. So I've worked at BAE Systems for 35 years, so it's quite a long time. And I think my tie, which I'm wearing this evening, is probably older than quite a lot of people in there. So I'll just mention that. So I'm one of your local network volunteers for the IET. I think I've done that now since 2000. And this is only a recent venture where I've become an education officer, which sounds kind of, well, quite high and technical, but it's not really. So I'll just go back to say what a facility this is. Wow. I was quite fortuitous. I bumped into Kurjan on one of our events, and I was just blown away with the actual facility. Every piece of equipment you got is absolutely world class. But not just that. The equipment, the building is fantastic, but it's the quality of your teaching. I must say, and I think we could do this now, a round of applause for your lecturers here. I think they do a fantastic job. Thanks. So part of my role really is help the students, help what I can do, obviously with my learning experience, the job I do. I've been an instrumentation engineer for 25 years. Prior to that, I worked on Tornado. I've done trajectory analysis on various stores, which is kind of different from a rocket, although missiles do have some sort of similarities. What I want to try to do is really give you a little bit of an insight of what working life is. Now, this society really, to me, sort of gives you a really good summation. You've got a group of students. Yes, you know each other, but not really that well. You've all got your strengths. You've all got maybe a weakness. Identifying people's strength and weakness. And a collaboration such as an event like this is fantastic. And what an absolute fantastic achievement to put on your CV. This is part of what you'll be doing in the future. This will be part of your bread and butter, working together. I was really, really impressed how many hours of dedication the students do. I can safely say the work and the involvement that I had was only a very, very tiny amount. The students just, well, their innovation and the enthusiasm really, really inspired me. And I really mean that. The majority of things that we do get at work, okay, we have major projects, but end of the day, the projects can't run without the people. And having a new set of students, new set of engineers coming to take over the mantle, for me, is fantastic. I get the inspiration from the students, really, more than anything else. The amount of hours they've done in this society, I was like blown away. You know, I mean, there is a small token that we've brought this evening from the IET, which is just really to show you a few CPD hours for the amount of effort you've put in. But really, that's insurmountable, really, for the amount of time that they spent. I've enjoyed really being part of it for the last 4 years in this fantastic, innovative centre. Hopefully, I can continue to do so for quite a few more years. I'd just like to say thank you very much, and hopefully next year there'll be another achievement on this board. And I did like the saying. I'm just going to just finish on this, if I may. Life is not linear. That is a I'm going to take that home. I'm going to take it to my work probably tomorrow. There's also things that happen where you'll be working on very expensive, very well organised projects, and everything will all be measures be put in place. There'll be plans. There'll be contingency. However, life doesn't work like that. Being a good engineer is knowing how to remedy those mistakes, and remedy them you will. Thank you.
Everyone. So at this point of time, we are going to invite all the guests to come around this edge. So there would be different awards given. So can I invite everyone individually so I don't miss anyone in their names perspective? So can I invite Paula Gill from Northwest Aerospace Alliance CEO, Professor Robert Walsh from Aerospace Engineering. If you can stand and leave a space between so that you can gather the students. Absolutely.
Okay.
And then Frederick and David and Paul and Darren and Charlie also to come on the stage, please, if that's okay. So if you can gather around, that would be amazing. So the students would be standing between.
Okay, I'll stand on this side then. We can stand there. Okay.
So that's from me, and the students are going to come and present the awards. So let's see how it goes. Thank you.
Thank you. Oh God, there's a lot of you. We'd like to start with the outstanding contribution to the NRC project. This specific individual was our design lead last year. He designed the vast majority of the working components of our rocket, and he, well, let's be honest, was the only one who really knew what he was doing. So that is Mr. William Butler.
There we go.
Well done. Congratulations. William, come back.
You've got to get a picture. Come on. And next up from NRC again, we have the Above and Beyond Award. So this gentleman has done far more than his job title of Avionics Associate last year. In fact, he is operating one of our cameras right now. Ladies and gentlemen, Ahmed Ijaz. There you go. Pass it down.
Congratulations. It's up in the middle.
Any trophy? Look at that. There you go.
Yeah, right, there we go. So next up is the NRC Commendation Award, or Outstanding Contribution. And this person has put in the time, put in the effort, and has often worked a lot behind the scenes and often not got any credit for it. So I'd like to give this award to Karis Field.
Stand here, we'll get to it.
So the next award, based on talent, the best new initiative, is someone who's came in, hit the ground running, and just got their head down and done really excellent work, and we thought we'd want to recognise that. So can Lucy Hall please come up to the stage?
Congratulations.
And last but not least, we have a few special mentions. These are people who have put in a lot of hard work despite not quite making the award this time. So we have Ariana Smith, who's currently our stage manager for this event. She also made all of our logos, so if you see those in our PDRs, that's all her work. Alex Gilmore, who's currently on the other camera, and Husnain Hussain, who is our manufacturing lead for putting up with all of our manufacturing requests, which there are a lot of. But so thank you for them. Let's have a round of applause for them. Thank you. So now we're going to hand over to Mac for their awards.
Thank you very much. Right. Right, have we got slides for this? We do, right, lovely. Whoa, nearly. So this award is for, sorry, if I actually hold it. Yeah, so this is for a person who's went above and beyond throughout the course of the MAC competition. That means everything from sort of your low-level workings of the rocket last year to understand how this functioned and how it worked, all the way to pulling 10, 12-hour days when it came to PDR, CDR presentations. This person has absolutely went above and beyond what would be expected of a normal team member. The level of effort which goes into a project like this really cannot be understated, especially in the last 2 weeks of the project. And also on the launch day, getting the systems ready and making sure that the rocket was in a good state to launch, and to do it faster than any other team at the competition, earns Brenda Acroff the Above and Beyond Award. So sorry to embarrass you.
Anywhere you like.
So next off, we have the outstanding contribution to the MAC project. Yeah, thank you, Brenda. Yeah, so the outstanding contribution to the MAC project. This is going to a team member who started off the project with absolutely zero experience in not only in high-powered rocketry, but also at university. Someone who didn't actually start off on an aerospace degree and actually changed his degree to learn more about the project. So to be honest, I think that really speaks for itself. This award goes to Archie Addis for outstanding contribution to MAC. Thank you very much, Archie. Well, they're both yours.
Can you fit in?
Can you change to? Yeah, then I'll tell you. So the last award for today for MAC is the Personal Development Award. And that's going to a student who not only has performed really well when it came to the end of the competition, designing the entirety of the rocket's independent payload on their team, but also, again, someone who started off with no experience in the project and also started off maybe without so much confidence, and was throughout the course of the project able to really, really improve on their skills to work with people, to work with our sponsors like we have on the Rocket Project, and to actually lead the CANSAT team this year. So the Personal Development Award for MAC 25 this year goes to Lily. Thank you. So finally, thank you. So finally, we've just got some special mentions from the team last year. Most of the team have now graduated. They were fourth year students at the time of the project. So I cannot understate how much work these guys have done for this rocket. From getting in at 7:30, 8 o'clock in the morning, the moment the building opens, waiting on security to come and open it for us, to leaving when the security man kindly allowed us an extra hour at the end of the day to finish. These guys have put in a ridiculous amount of work on the rocket. In the competition, these guys were up until 4 o'clock in the morning trying to get the systems working. We've been in the composites workshop, machining, working with carbon fibre materials that we had absolutely no experience with. So there has to be a special mention to all of the fourth year students who were on the project this year. So we've got 2 names up here, but that doesn't describe the amount of people who are on the project. So Samir Shazad, Andrew Durzu, Owen Lynch, Robert Bradley, Benjamin Brilski. Put your hands up if I've missed you, please, because I can't remember all your names. But thank you very much for your work. It's resulted in something that I think is absolutely incredible. Yeah, that is it for MAC. So we'll move on to UAS. Good, thank you. You ready to give this? One of you guys can give them as well. Oh.
All right, so our first award goes to someone who came in at the start of the year with no prior experience in engineering. And this person made a lot of progress from start to finish. She basically took on the role of our avionics lead, having zero, I've never done it before. This person is Rachel Loftus. Our next award is for the Excellence Award. This person always showed up, was there probably more than any of us throughout the week. From Monday to Friday, long hours, especially after university finished, even though his family lived very far down south. He definitely put the effort in and it definitely paid off. So this award goes to Aryan Das.
Well done.
So the next award is for the personal development. So this person came out of her comfort zone and kept the group intact when we were kind of lacking behind. And So we had this business presentation, and we didn't have a presentation or anything ready. And she actually did it in a day and presented, and we got third in our presentation. And I'm presenting this award to November. So next is the special mentions. So we got Josh, who was our team lead, who, same as Tino, so he actually went above and beyond to keep our team, like as a team. And then we got James, who was our design lead, who picked up our team when actually it was going down the hill, and designed a fantastic plane, which actually flew. And then we got Ray, who helped us with all the manufacturing, and who, same as Aryan, he was here every single day, 9 till 7, I would say, and some days even 7 in the morning, even though he's not a morning person. Yeah.
Thank you very much.
Can we have another round of applause for our award winners? One more round of applause for our award winners here. Thank you very much. Okay. Now we are going to have our last guest speaker of the evening.
Yes, it is Paula Gill from the Northwest Aerospace Alliance.
Did you have any?
So good evening, everybody, and thank you for the invitation. It's a very special evening. But there's one thing that I want to hear from you all before I start talking properly. And once I start, I don't stop, I'll just warn you. There's been a lot of inspiration that's come out of this tonight, watching the activities and seeing what's been achieved, and some wonderful awards for wonderful people. But what I've not heard is those screams and those yells and those congratulations. So come on, guys, let's hear it. Let's hear it for all of you. Let's hear it. There's been some phenomenal achievements that we've been seeing here today, and it makes me very proud. So for those of you that don't know me, my name's Paula Gill. I'm the Chief Executive of Northwest Aerospace Alliance. What is the Aerospace Alliance? It's a trade association that works with businesses in aerospace and defence around the north of England. The large, the small, the innovative, and the family-run. All of these businesses that sit on your doorstep. The reason I'm here and I'm involved with the university, I sit on the Industrial Liaison Board. I'm currently acting as the chair, and my job is to work with the teachers, the lecturers, sorry, not teachers anymore, you lecturers, because everybody's a bit older now. I'm still back there. With the businesses, the investors, we're going to look at, as we talked about earlier, some sponsors and the students. This is not just about what you're doing here today. It's not just about the achievements. This is one step on your journey, and this is a huge step. It's huge. Don't ever underestimate the activities you do here, the work you put in, and the achievements that you make. But this is all about the life plan and the next steps. And for me, that's where I come in. That's where this is important to me. I need to go into the world in the north and tell the businesses out there, the primes, the small businesses, the medium businesses, the innovators, who you guys are, what you guys do, the things that you achieve. the activities that you participate in and the effort and energy that you put in. The passion that comes from you guys that says, actually, the next generation of engineers we've got coming through are the best yet. And we want to make sure that we keep you in our industries and that our industries see you and recognise you and want you. They want you in their businesses. So that's why I'm here today. There's been a lot of messages that have been left, and I'm not going to go on, I'm not going to harp on. I've got a couple of messages. The first one is this. I am very, very proud to be stood here today, to actually even participate in this and have the honour of speaking to you all and meeting you all and seeing what you've done. I will take all of these messages and this information and these projects. I do keep my eye on these projects, by the way. I do know what's going on with these projects. So I had a bit of inside information as to what had been happening and who'd won what, and it's phenomenal. I love it. I usually cry when I'm over-inspired by young people doing great things, but I've done really well today. I've not cried at all. So I'll give you that challenge to try and make me cry later. But I want to take you guys and this information back into industry. But the message I'll leave you with, because everybody else has given you a good one, given you something to take away, sorry, is do not go where the path may lead. Go instead where there is no path and leave a trail. And you guys, for me, today, have shown that you're already doing that. You are the trailblazers. You are the next generation. And again, I want to say congratulations and thank you very, very much.
Sorry, we have got one more person to give an award. I think we missed it, so we are going to try and give that as soon as possible. And then I will have a closing ceremony with a few people to mention. I will do the award first and then. So we have got above and beyond award for Alex Morris because he has done a lot of work in iMaker US, Rocket in Mac competition, and you can see a lot of things. I am grateful. I would like to especially thank John Pinder in this matter, if he can stand, because I think he also needs a round of applause. Because sometimes we forget those people who are role model to us and we just fly away, but thanks to John, without his support it wouldn't be possible. Also, I'm going to give the award first and then I'll continue. Can I invite Alex Morris, please?
Well done, nicely. Congratulations.
Thank you. I wish someone would have told me. Thank you.
So at this point of time, I would like to thank few people, but I would like to invite my fellow colleagues. This event wouldn't have been possible without few key members in my team, my colleagues that I would like to thank. If I may ask, first of all, one of my pillar of support in this society, Gonzalo, to come forward, please. Because without him, it is not achievable what we have achieved. I think sometimes we have to think as a team. We are a great team from the start, and special mention for two people. But before that, I will invite John Pinder to the stage as well, please. He's another colleague who has achieved this. Another fellow colleague of ours called Ben Watkinson. He's not at the moment in here, but he's a great help from the start that we started this Aerospace Engineering Society. But last not least, there's another gentleman who was Darren's research fellow. He's no longer in this organization. Special mention for Aditya Sujit. We can't forget the basement that has been put to achieve this level. Finally, our Professor Darren Amsel, because times I have gone to him for money. It is saying, can I get a favor? Can you help us on this XYZ? last but not least, Paul Klitschik, the Allies technician team head. Without him, small bits, even in terms of pushing our agenda forward. And finally, Louis at the end, who's our operation manager. Can you wave your hands? This whole setup was done because of him. Thank you very much. And I'm going to close this ceremony at this point of time. There's more networking opportunity with key speakers and everyone. And there's tea and coffees at the end. Please be responsible and enjoy. Have fun. Thank you. Crew to the stage because this idea initiated from him and Shay. Can I come ask them to come forward here? With their initiative is what we are achieving today. So we are looking good because of them. Can I please invite all the crew members who are behind the scene? Can I will hold the camera.
Come on, come on, everybody up, come on. Thank you all for coming. Have a good night. Photo, there's a photo. I'm not going to move.
Try to understand, and there are times of